Hello and welcome back. If you follow the channel, you know that we are attempting to restore this gorgeous HP182 oscilloscope from 1972, part of the HP180 series of early high-performance transistorized oscilloscopes. We spent the two first episodes recovering from an incident. It happened while we were adjusting the high voltage power supply. But I swear, officer, the HV power supply attacked me first. Anyhow, we recovered after much difficulty, and we now have a fully functional and calibrated mainframe with a gorgeous blue phosphor screen. It's time we pay attention to our horizontal and vertical plugins, neither of which are working correctly. This set of plugins is the original pair released with the HP180A scope in 1966. For being so early, you'd think they'd be weaklings with primitive designs and limited performance. But you'd be oh so wrong. The HP1801A vertical plugin is a dual trace unit conservatively rated to 50 MHz at 5 mV per division sensitivity with the full complement of AB display, chopped alternate, AC and DC coupling, normal and invert, and even add and subtract modes for differential probing. The horizontal unit is equally impressive. It's a dual delaying Timebase with two independent sweep rates, both independently triggered. 22 sweep ranges for each as fast as 10 nanoseconds per centimeter sweep rate. It's entirely made out of discrete transistors, a gajillion of them. But as you'll see, the complexity, maturity, and analog wizardry of its design is impressive, not something you'd associate with the year 1966. No wonder they went to the moon with that breed of electronic engineers around. Sadly, neither of our space race era plugins work correctly at the moment. The worst offender is the 1821A Timebase, which doesn't even sweep. Okay, we do see an occasional sweep sometimes if we jiggle the knobs the right way. So at least it's not entirely dead. Alright, so after replacing all these bunches of components, we finally get to where we wanted to be, which is repairing the Timebase here. So the trigger not working, which is going to be amusing because the trigger on that one is particularly tricky with the infamous tunnel diode system. Okay, the educational material, I have the manual, is somewhat limited in its description of a circuit. Exactly, they don't do a circuit description, they just do block by block. The Timebase is quite a complicated unit, but thankfully I acquired a manual with the full schematics. However, the manual doesn't have the usual detailed schematics explanations, so we'll have to make do with this high-level block diagram. All the triggering sources are fed to the main trigger generator. Its function is to generate a sharp pulse at a precise triggering point in the waveform. That's the circuit that uses the mysterious tunnel diodes. It is followed by a gate generator. This circuit outputs a simple square wave. It goes low when it receives the trigger pulse, stays low for the full duration of the sweep, then goes back high at the end of the sweep for the traceback. Its output controls the gate amplifier that we repaired in episode 2, which is really the beam blanking control. It makes the beam visible for the duration of the sweep and otherwise blanked during the traceback and the waiting period. The gate also releases the main integrator. This is the circuit that generates the sawtooth signal that sweeps the beam horizontally. It is implemented with an analog integrator circuit, hence the name. The main Schmitt trigger is the logic control. It detects when the beam has reached the end of the sweep and turns off the main gate. It also controls when the main gate is able to be re-triggered again with the help of several ancillary circuits. The hold-off circuit, marked HO, prevents the Schmitt trigger from releasing the gate too early during the traceback. The auto circuit is kind of the opposite. It will trigger the gate if a normal trigger is not received after a while, so that a trace can still be observed even when not normally triggered. The whole thing is duplicated for the second delayed Timebase. Right now the main sweep is never triggering, neither in normal mode, line mode, or auto. I suspect that the main trigger generator is not working. this seems to work because we see the trace and then it resets it. So I suppose it's the main trigger generator that's not doing good. So we're going to go to the schematics there. Wow, the number of adjustments on that board is quite amazing, and actually you can tell this board is just chock full of adjustments. So I set myself up to debug that section, which is the trigger generator. Alright, since HP did not provide a detailed schematics explanation, I'm going to do it for you. All the various triggering sources eventually make it to the input of JFET transistor Q103. It's wired as a source follower, so we should just get a nice copy at the output, which we'll measure at test point 1. JFETs are fragile, so it could very well be that it is blown, causing our fault. So it starts in here with a JFET supposed just to amplify the signal, which is a sine wave at the moment. This should be my signal. I have a beautiful sine wave. First stage working fine here. Great, the JFET input stage is good. It then feeds a comparator formed by transistors Q104 and Q105 arranged in a long tail pair. It compares the trigger input with a DC voltage that you set by twiddling the trigger level knob. The trigger level voltage goes through emitter follower Q106, then hits the other side of the comparator. Out comes a pseudo-logic level that should be the binary comparison of the two, which we'll measure at point 2. And then it's getting to a comparator, which is going to compare it with a reference voltage. That's where you choose the trigger point, and that's my second test point down here. And oh, I think it's comparating. And if I change the trigger level, it's moving. Oh, okay, that is very promising. Well, that is also working a treat. Let's move on the magic trigger generator circuit. The magic should be performed by the tunnel diode CR106 followed by amplifying transistor Q107. That should add a very sharp pulse to the rising edge of the comparator signal, which we'll measure at point 3, which was missing from the manual, by the way. Then comes the party trick, which is the tunnel diode. So the tunnel diode, they are a little bit mysterious to me how it works, but they are supposed to generate a super sharp edge. Ooh, it's so sharp, it's barely visible. There it is. So here's my sharp edge. So if I go back here, you can hardly see it. And okay, super sharp edge. Phew, our magic tunnel diode works. I don't have to debug that, fortunately. The next piece of signal processing is done by C119, a very small cap that forms a differentiator with R137 and is going to filter out just the sharp pulse, helped by transistor Q107, which we can measure at point 4. And then there is a final stage which just keeps the very sharp pulse, and that's going to be our trigger out. So that's going to be the acid test. And at first you say, well, it's not working, but it's working super well. It's just so fine you don't see it. There you go. Let me do a single. There it is. Poof. I have this beautiful 2-volt pulse. The trigger signal is working fine. So then we go to the next page where it develops the starting gate, and I bet you, since it's not starting, we are going to come in trouble somewhere in here. Ladies and gentlemen, welcome to the next page of obtuse schematics, where even more wizardry awaits. Our nice trigger pulse arrives from the previous page. It is then added to a signal that is the output of a Schmitt trigger formed by Q204 and Q205. Then it is processed by one more of the magic tunnel diodes, CR201, which I think acts as a bistable element. I think that the tunnel diode is what opens the gate by the magic and witchcraft of negative resistance. It's sort of a bistable digital output controlled by an analog signal. We should get a gate signal at TP201 or triangle mark 1 right on the cathode of the second tunnel diode. And at this point, I am not so hopeful. So here's our trigger pulse. And there's another of those devilish tunnel diodes. And we are supposed to get the gate signal. So let's move on there. And by the way, the tunnel diodes, they are this weird component right here. This little weird golden fellow, that's the tunnel diode. So we move on to the next tunnel diode component, blue, and we get it here. Let's see if we have a gate signal. Go back here, and we do not have anything. So why am I not surprised? So no gate, nothing's happening. This is unfortunately the trickiest part of the schematic. Could be either the tunnel diode that's giving us a problem. It could be that the Schmitt trigger is stuck the wrong way. Alright, after studying this, I think this is set all the time and never reset. That's my problem. And one way to test if it's reset would be to press the reset key. So if the Schmitt trigger is in the wrong state, it will prevent the gate from opening, and I'm thinking that maybe that's what's happening here. But switch S201, the reset button, should enable me to reset the Schmitt trigger manually. Let's try that. Weirdly, it is tied to a neon light that's an internal component, probably used to generate a pulse when the neon strikes. Smells like a remnant of tube circuit design to me. If that's true, maybe we'll even have some visual feedback. And I was looking at the schematics, a reset key, and there's a neon bulb in there. And yes, we have a neon bulb right there. I turn on the thing, I'm going to press the reset key, which is on the front panel. Does it light up? Sure enough! So the reset key works. However, once it has reset this, should get my reset lamp working, which is over here on the key itself, and I'm not seeing it. How nice of them, they have put another neon light indicator, which I think should give me the state of the Schmitt trigger. But I'm not seeing it light up. So I went to probe transistor Q203 that controls it, and that's when I noticed something was not quite right. And Q205 is down there. It looks smashed in. It looks like it has been pushed in and that the leads are touching the can. We would be lucky. That's all we need to do. Yeah, this is completely smashed in. There's nothing protecting it once it's out the instrument. So, okay, it's a little bit hard to see if I did it right or not. So, no. I see the light lighting up back there, but still nothing here. Okay, so it wasn't that simple. Dang it. Well, a shorted lead on Q205 could certainly have resulted in getting our Schmitt trigger stuck. But no, that was not the case, or there is more than one single fault in our instrument. And to add insult to injury, that's when yet another disaster struck. Alright, in the series, what else could go wrong? While I was off camera, I was trying to figure out if I could get it to reset in single sweep mode. And while I was doing that, I heard a distinct small pop towards the back of the instrument. And then all of a sudden, I lost my comparator. If I do reset, I don't have my neon shining anymore. And I went to check the power supplies and I'm missing one. I'm missing the minus 100 volts. It's not the fuses. The fuse is good. So, gee, now we have a minus 100 volt power supply problem on top of all the ones we had before. Okay, a little update on our power supply diversion. So I started to test all kind of things. The output transistor was fine, all the other transistors looked great. The pass transistor, that was fine. I took it out and put it on the transistor tester. Alright, in the series What Else Could Go Wrong, I lost the minus 100 volts power supply after hearing something pop. I first thought something had gone bad in the power supply itself. The supply is a simple linear supply, there isn't much to it. But all the transistors checked good. However, these power supplies have a current protection, here implemented by Q14. So I thought maybe the power supply is fine, but something popped in the plugins and is causing an overcurrent and triggering the protection. And sure enough, that's exactly what happened. And then I say, well, you know, wait a second, the thing brought our power supply down and the current protection is kicking. And sure enough, I did slide it out and I have minus 100 volts. So something else blew in that thing and it made a noise, so a cap or something. It could be either of those two modules, so an easy way to tell. So you pull the thing at the back and off you go. There you go. Let me plug that one back in and see if it brings the power supply down. I didn't hit the record button when I should have, but the short is confirmed with this triggering unit. So one more tidbit of information. I thought the fault would be between 100 volts and the ground, but it's not. It's between minus 12.6. So the minus 100 and minus 12.6 should have nothing to do with each other. So it can't be just a cap to ground that blew. It's something else. Alright, mystery intensifies. Minus 100 and minus 12.6 go everywhere. And I tried to disconnect every wire that had it on it. And I still had the short at the input, so I completely disconnected that board. Nothing happened, the short's still there. And this board is really hard to disconnect because there's stuff on the bottom. So I sort of gave up. I'm trying to smoke it, so I put 11 volts and an amp into it and see where it goes. And it becomes smelly over here. And the 1 and the 2, I'll power it up. Ooh! One component will get pretty hot here, right there. So the one that gets toasty is this guy. And then I go in the component map, try to find which one that is. It's not a diode, it's a resistor, but on my board it is certainly a diode. So R256, so where is R256? And R256 is here, and even worse, it says it's not connected to anything. What? Then I looked at it some more, and you can tell it's a workaround. It has been replaced. This has been changed and this one has been changed. It blew up in a part of the circuit that's not supposed to have a diode. At this point I'm totally confused. What I can do is remove that. This is in the delayed time base. That shouldn't affect us too much. Alright, so while you were not looking, I disconnected it. By the way, I don't even think it's R256. R256 would be here, and there's nothing there. It's just something's been added where it's not supposed to be. Anyhow, now it's not there anymore. And guess what? My short is gone. No beeps. If I do the smoke test, no more current through it. I'm going to reconnect everything and see if we get back to something that makes any sense. We have minus 100. Okay. We are temporarily back in business until the next catastrophe happens. And oh, we're back, baby. So, okay, before we had our incident, we checked that trigger was working up to here, and it's working now again that we have removed the offending component. Before I go off to the other page, I wanted to check this part of the circuitry. That is for the auto run. My worry is that it interferes with triggering. So we're back on the first trigger schematics page. There are a bunch of additional circuits that I like to check since they could interfere with our trigger pulse. These are the auto trigger circuits, and auto triggering is not working. I think this monostable multivibrator gets set every time a regular trigger event happens. As long as they are regular triggers, the monostable multivibrator output will keep the lockout transistor Q112 on, which will short out transistor Q109 and prevent any free-running auto triggers. But if there are no triggers for a while, the monostable multivibrator expires, the lockout transistor is turned off, and Q109 springs into action. It must then create some artificial trigger pulses from a signal coming from the next page. I gather something signaling the end of the flyback, which would be the appropriate time for auto triggering. Let's check that out. Then if we are not triggered for a long time, the free run lockout gets turned off. The free run generator generates trigger. I hooked myself up at Q111 over there, this fellow. And I expect different behavior depending on which trigger mode I am at. I am in auto and I see something happening each time we have a trigger. If I undo the trigger, yeah, the multivibrator stopped, it relaxed all the way to minus 13, 14 volts. That should now allow the auto pulses to come through. So I now know that this is working. So I hooked myself up to the collector of Q112, and that should tell me what is the lockout condition. So now I'm triggered. Lockout condition is minus 13 volts. So that's when the auto circuit is disabled. And now 0 volt is when it's enabled. Okay. Seems to be working. This should be released, and then this stage should spring into action. It should auto trigger, which I don't see it happening. And I bet you it's because I don't have auto triggering coming from the other page. But we can check that. So it's the blue probe. So blue, I see nothing. I should see something if it was sweeping, but it's not sweeping. And now I am in the auto condition. I see absolutely nothing coming back. So, which tells me something is not coming back from the next page. All right, so off to the next page we go. So it might look like we're not making much progress, but we are. We now understand the first page of schematics fully, and it has been thoroughly checked. Everything in color here is working as it should. We are now pretty certain that our fault is further downstream on the second page, so let's continue exploring that. Here's our second page again. Except from the trigger pulse that's generated from the previous stages, it's a self-contained circuit arranged in a giant loop. As we saw before, the output of the loop, namely the output of the Schmitt trigger, gets added back to the trigger pulse. Last we looked, we saw nothing, but now that the first page has been fully exonerated, I'm starting to doubt that. Let's recheck that we at least get our trigger pulse all the way to TP201. Okay, so that's where all the magic happens. The trigger pulse is mixed with what comes out of the Schmitt trigger here in this magic tunnel diode. And there's a test point. And they tell us what it should look like. It should look like this, but I have no sweep, so I don't expect very much. I think we will see absolutely nothing there. And nothing. Oh yeah, I see it. Yeah, I see the trigger. It's very fine, you can't see it, but there's a little super small line there. So I see the trigger pulse, but then the trigger pulse should trigger a whole bunch of events through this loop. And it doesn't. Oh no, after foiling the plot of the blown up diode that should not have been there in the first place, and the smashed in transistor plot, we've met our nemesis again, the loopy circuit. These are notoriously difficult to debug, as the fault could be anywhere in the loop. And on top of that, it's a loop with at least 2 additional sub-loops in it. As the fault propagates around and takes down the entire loop, it's super hard to tell where the problem originates. It is guaranteed to be a major headache to figure it out, so we'll take a break here and try to tackle it in the next episode. But dang it, it's all discrete standard components, so we should eventually be triumphant, right? And we could not possibly make it worse than it already is, right? What the... Maybe I take that back. See you in the next episode.